I guess it's worth summarizing what we've done so far, right? We're looking at circular restricted three-body problem. And we've said that there are energy cases. There we go. It's a pretty cool GIF. So this is showing the energy, right? We're showing a slice, and as it goes through, that's giving the zero velocity curve. So it's sort of giving the bounds of where a particle could go. And once you have an energy above negative 1.5, then the entire plane is open. So we're just looking at the planar circular restricted three-body problem. These necks open up around L1 and L2, and that's sort of our main concern, is looking at a case like this, case 3. And the main thing that we've talked about for how you go between different realms, the realm around M1, the big mass, the realm around M2, the smaller mass, and then the realm exterior to them both is through tubes that are stable and unstable invariant manifolds of periodic orbits. And today we're going to learn how to compute those. And I'll even do a little MATLAB tutorial. I'll share a live script, and then I'll post it in the Google Drive so you guys can see it. So here is a depiction showing the periodic orbit and tubes in a three-dimensional projection of the four-dimensional phase space. So this is showing there's a periodic orbit, right, where these necks open up. And if we were to look in phase space, there's these tubes that are related to every point along the periodic orbit. We can find a stable and unstable direction, and then you could compute a trajectory. When you can connect all those trajectories, you get a continuous thing that has the geometry of a tube in phase space. So this nicely depicts that if we looked at this Poincaré section over here, it calls it U1, but it's not related to what I called U1 before. It's just a surface of section. And on that, there's an inside of the tube and an outside. The red trajectory is on the inside, so it transits from one side to the other. And then the blue is outside. It starts outside, so when it approaches this periodic orbit, it starts bouncing back. And then we just stop the integration. So the key thing we're going to talk about today is finding these periodic orbits in the planar problem, and then computing just computing along the stable or unstable manifold. If you can find a single trajectory, then you could actually find the entire continuum of trajectories. That's the goal, and that's what we're going to talk about. So if we want to find a periodic orbit, and I'll focus on, say, finding a periodic orbit around L1. So in the planar circular restricted three-body problem, let's find a planar Lyapunov orbit. It's a periodic orbit about L1. And when I do the numerical example, I'll use the mu for the Earth-Moon system, which is pretty large. And why are we doing this? We want the periodic orbit so we could eventually find the manifolds. But you saw how we in an earlier kind of MATLAB tutorial, I used the eigenvector approximation to find an initial guess of what an initial condition on the periodic orbit would be. And it wasn't perfect, but I guess you could say it was better than nothing. So how do we get, I'll call them initial guesses. How do we get an initial guess for a Lyapunov orbit? And there's a few different ways. There is something called Poincaré-Lindstedt method, which sort of falls under the category of a high order analytic expansion. It doesn't have to be super high order, but instead of just looking at the linear terms, you include higher order terms, and you can do this. So that's called Poincaré, Lindstedt, and if or when we get to halo orbits, this gets used for halo orbits. There's a good third order approximation which gets used. There's something else called normal form theory that can be used to find periodic orbits and also quasi-periodic orbits. The one that I'll talk about is, I guess you could think of it as kind of brute force, but it has some elegance to it. And that would be numerical differentiation or numerical differential correction. I guess that wouldn't be necessarily an initial guess. This would be an accurate periodic orbit. And this is what I'll do today. All right. So the idea is we want to get a periodic orbit, and I'll call it X bar. So we want X bar periodic orbit. So that means that X bar of T is X bar of T plus capital T, where this is the period of the orbit because it's periodic. And we'll use something similar to what I talked about in an earlier lecture. If you remember lecture 5, that was about motion near L1 and L2. And I talked about the linearized dynamics near a reference orbit. So let me just give a little refresher on that. And that'll get us going. Let's start with finding the linearized dynamics near a trajectory, any trajectory. So this was the situation where we've got x dot is f of x. That's our equation of motion. So this would be in Rn. We've got, for the planar circular problem, n is 4. And if we have a solution of interest, we can determine local dynamic stability. We could do other things. But let's say we have a trajectory of interest. And I'll call it the reference trajectory. So here's a reference trajectory. X bar. And if we have some other nearby trajectory, we'll show that. There would be an initial displacement. So I'll call this x of t, and it's going to be the same as x bar of t plus, and now I'll call it delta x t. That's the displacement. So x bar plus this displacement that we're calling delta x. So this is delta x, say, at time 0. So this would be x bar at time 0. This is x at time 0. We want to know how this displacement vector grows. So at some later time, our displacement vector has changed. Maybe it's growing, maybe it's shrinking. And we figured out earlier how it grows, and at least to leading order. So to leading order, what did we get? So this would be the equation of motion for the displacement vector. Delta x. it evolves as delta x dot equals df. So that's the Jacobian matrix along the reference trajectory, and then delta x. So this is a time-dependent matrix. Now, if we, and it's n by n, so this is a n by n time-dependent matrix that we usually obtain numerically. You can't typically analytically get this. These equations, I don't know if I called them this, what they were last time, but these are called the variational equations. Delta x, and instead of being called the displacement, is sometimes called the variation. And if you were to follow this from some initial condition to some later time, the solutions of this are known. So solutions are of the form delta x at time t is a matrix, I'll write it that way, capital Phi, just delta x at time 0. This is called the state transition matrix. Or STM. So this is it's the state transition matrix from time 0 to time t. So this is an n by n matrix that encodes information about the dynamics along the trajectory. It, in fact, tells you things like if I started with, like up above, by a delta x 0, and I wanted to know how that grew. So how does it grow or shrink? But in this case, I'm showing something growing. So delta x at some later time is going to be that state transition matrix times the initial displacement. And a different displacement might not grow. It might shrink, or we could get other types of things. So to calculate this state transition matrix, we calculate a version of the variational equations, but one that's appropriate for phi. So this is how we do it. So the state transition matrix along a reference orbit or reference trajectory doesn't have to be periodic yet. We haven't said that it's periodic. This is for any trajectory. This is computed numerically by integrating n plus n squared ODEs. And these ODEs are typically you don't have the reference trajectory analytically, so you calculate the reference trajectory. So that gives you n ODEs. And then you calculate phi dot And phi dot is equal to this Jacobian matrix along the reference trajectory times phi. So since phi is n by n, that means these are n squared ODEs. And so you do the two of them simultaneously. With initial conditions that x bar of at time 0 is some initial condition, I'll call it x bar naught, and the initial phi, so capital phi 0, 0. This is the identity matrix, the n by n identity matrix. Because if you haven't, if there hasn't been any motion, that means that right, phi or delta x at time 0 is going to be phi 0, 0 delta x times 0. So that means this has to be the identity. If we're looking for a periodic orbit, so if the initial condition is on a periodic orbit of period capital T, then we would use capital T as the final time. And the final conditions will be following. If we're really on a periodic orbit, then x bar at T will be the same as x bar times 0. So that would be the same as the initial condition. But phi of capital T 0 does not equal the n by n identity. It's something else, and we call that something else the monodromy matrix. So we end up calling this something. It's often represented by M. And the monodromy matrix encodes information about the stable and unstable directions along the periodic orbit. To do differential correction, we won't necessarily use it for that, but that is what it gives. Let's see. Let me see if I can do something here. Yeah, if we're close to a periodic orbit, so if we have an initial condition, maybe it's an initial guess that's not exactly on a periodic orbit. So close to being on a periodic orbit. So let's say we've got, here's some initial condition, and maybe it goes around and doesn't exactly come back to where we thought. Let me erase that and call this x bar naught. So this would be the displacement after a time capital T. So maybe we have a guess for what we think the period is. Let's just call this time T. So this would be x bar at time, we'll call it T1. T1. Then we're going to have some displacement. I'd call that maybe delta x T1. So delta x of T1 is going to equal phi T1. Let's say the initial condition was at time 0, delta x time 0. And we want to drive delta x t1 to be 0. So we use something that's called a shooting method. In fact, that's what differential correction is. We want to adjust our initial condition in order to reach a desired target point at time t1. So that's what we want to do. What do I have here? Yeah, so let's say x bar at t1. That's our x desired minus delta x at time t1. So to use it, maybe it's not very technical, we wiggle our initial condition to reach some desired end state. In this case, we would like that x bar of t1 equals the initial condition. And how can we do that? Well, we use this differential correction thing. So we have 1, 2, 3. Yeah. We can use this and just write the inverse of it. So delta x at the initial time is equal to the inverse of that state transition matrix times our displacement at time t1. And you can use this because you'll calculate what your final displacement is. So delta x t1. You want to drive delta x t1 to be small. So this tells you how do you pick this to cancel that out. So there's more details in the book, but we'll implement this. I've got some code that'll implement this and find a periodic orbit. In fact, what we do is we use a symmetry of the three-body problem along the x-axis. If you start with some initial condition that's on the x-axis and has only a velocity in the y direction, and then you follow that initial condition, there's going to be a mirror image trajectory that's going the opposite way in reverse time. So there's always some kind of mirror image trajectory. So if you have a trajectory that hits the x-axis exactly perpendicularly, then that means there's a periodic orbit. So we really only have to look at 1/2. So I've got something that implements starting with some initial condition. We look for the first x-axis crossing, and then we're trying to adjust that so that it only has a velocity component in the y direction. So it's numerically more stable than actually following completely one periodic orbit. It works for this case because there is a symmetry. We can do this because there's a symmetry in the three-body problem. So if we have a trajectory that, say, is a little bit off and it hits this and it's not perpendicular, well, we need to adjust that, right? And so this will kind of go the opposite way. And then it'll finally converge. You can get convergence usually within a few iterations. What we're trying to do is drive that, like I said, the x velocity to equal 0. There's a question? Yeah.
Yes, Dr. Ross, if can you still do that method if if the duration of time isn't long enough to cross the x-axis, if it's, say, it's a shorter period of time, or if is it in that case it's so short that you don't really even have this problem to begin with?
If it's so short, then the algorithm just wouldn't work. So you need to get an x-axis crossing, at least for the method that I'm using. If it doesn't cross the x-axis, the method wouldn't know what to do.
Okay,
so you need to pick a time long enough that there's at least the way I have it, it looks for one and only one x-axis crossing. So you could have something that maybe comes back and hits the x-axis, but it's just looking for that first x-axis crossing.
Okay. Oh, so you can't even have more than one. You need to be exactly one. Okay.
Yeah.
Thank you.
Yeah. I mean, there's probably other methods for finding other types of periodic orbits. This is specifically for the planar Lyapunov orbits. So we'll implement this in MATLAB. And we'll do that in a little bit. I want to say after we find that, what do we do? So once you have something where x bar time t minus your initial condition, let's say you make that magnitude, you look at the magnitude of that, and you want that to be small, so within some tolerance. So usually we set some kind of, that's supposed to be a less than some tolerance. And for the non-dimensional restricted three-body problem, I think I typically take this to be, so we're looking at the norm of the entire phase space difference after we've gone through one period. I typically want this to be around 10 to the negative 10. It's just a rule of thumb. It doesn't mean it has to be that way, but this seems to work. Or it looks nice and gives good results. Once we've done that, then we can calculate that monodromy matrix. So then we get the monodromy matrix. Which is phi going from 0 to capital T. And this n by n matrix, in this case 4 by 4 matrix, we look at the eigenvalue spectrum and we can get corresponding eigenvectors. What we'll get for this, because this comes from a Hamiltonian system, there's going to be a certain type of eigenspectrum. The eigenspectrum, it's going to have, there's going to be an eigenvalue 1 that has a corresponding eigenvector that is the tangent to the orbit. So it's just the direction along the orbit. So this has an eigenvector that's along the orbit. There's another eigenvalue 1, and this corresponds to, or the corresponding eigenvector is pointing to nearby periodic orbits. On nearby energy surfaces. And then we'll get an eigenvalue lambda, which is going to be real. And just because of the three-body problem, this is going to be typically much greater than 1. And then there's going to be 1 over lambda, which will be much less than 1. So the eigenvector here, this corresponds to directions where you get the maximum growth. So if you start with some small displacement, it'll grow by a factor of lambda. So the eigenvector of the, I guess we could just say the stable or unstable eigenvector. So this is the unstable. And this other one, whatever your displacement is after you go around one period, it has shrunk by a factor of lambda. So this is the stable eigenvector. So maybe we would call this, maybe I'll call this EU and this ES. Just these are directions that we get. If you want a picture of what's going on, I think a picture would be something like this. Think of, maybe I'll make this bigger. Think of it as we take a slice or a Poincaré section, and this is showing the periodic orbit. So this is our periodic orbit. And I'll call this our initial condition, x bar naught. If we're along the unstable direction, then that means if we start with some small delta x, after we've gone around once, this is going to grow. So it'll be in that same direction, but now this will be delta x after time t. It'll be approximately lambda times delta x of time 0. So you get growth. Now, imagine this is repeated. That same thing, after it goes around again, will grow again by a factor of lambda. And lambda, for what I've seen of typical Lyapunov orbits, is a factor of 1,000. So that means any small displacement from the periodic orbit grows by a factor of 1,000 after one orbit. But if you're along the stable eigenvector or stable eigendirection, then it'll shrink by a factor of 1,000. Of course, any kind of arbitrary displacement is going to have some projection in the unstable direction, and that's why these are called unstable periodic orbits. There's a couple of other nice illustrations that might help with this. Where is it? This is from a book by Steve Wiggins. So he's depicting the same thing. There's a periodic orbit here. And if you wanted to visualize these things that he calls W, this is just like the continuous version of what the stable and unstable directions are along the periodic orbit. So this shows an initial condition, x naught. This gamma, he's calling the periodic orbit gamma. And then we have unstable directions, right? There's two branches. This even shows some curvature, not straight lines, because if you follow these things out, they will curve. And then there's a stable direction. So this, you could view, that's what's going on. Another depiction be this. So this should be reminiscent of when I showed that McGehee representation. It kind of looked like this stuff. So you've got the periodic orbit that's kind of in the middle of the X, and you've got directions where things are leaving the periodic orbit. That's the unstable manifold, and directions where things are approaching the stable manifold. So the way that we can get these is you would actually start, let's call this the initial condition x naught. If we wanted to get something on the stable manifold, so let's say along this branch, then I would just pick something that's distance epsilon in that direction. So this direction is ES. So we would take an initial condition, I'll call it x0, and we choose it to be the periodic orbit initial condition plus some small amount along the stable eigenvector. So this will be an initial condition along the stable manifold. And typically you pick epsilon to be something very small. Maybe I would use something like 10 to the negative 4. Some of these things just require that you turn some knobs and play with things and see what you can get. All right, I think we've got enough to actually start computing this. If you let's see, what am I going to do? I'm going to numerically look at the Earth-Moon system, and we'll look at L1. Start with an initial guess that comes from the eigenbasis approximation. Remember, there were stable and unstable directions, and then oscillatory directions. So I'll start with some initial condition that if I were to integrate it one full period, it probably doesn't come back exactly. But it's close enough that my differential correction procedure can find an actual periodic orbit. And then once we find that periodic orbit, so let's say once we found something that comes back to within some small tolerance, now we'll find an initial condition that's along the stable manifold and calculate that. So if we were to calculate something along the stable manifold, maybe we'll get something that goes back around the moon or something. And if we were to now start from there and go forward, we would have something that's asymptotically approaching this periodic orbit. This is just one part of the stable manifold, one trajectory on it. There's a whole continuum. You can get that whole continuum by just looking at different initial conditions along the periodic orbit and doing the same procedure. If there are questions before I go to the MATLAB. Let me try to fire up my computer here. So I'm hoping you can see my screen. So this is a live script, and I'm using some kind of legacy code from last millennium that I developed. So it's not very good about using global variables in the right way or anything. So this works. So I'm doing the same thing from before where we use the mu of the Earth-Moon system. And we get the polynomial to tell us where is L1. We take the only real root from this quintic polynomial, and that gives us gamma 1. And then we can find out what's the x position of L1, and it ends up being around 0.837. And then I'll get in the L1 eigenbasis, we can compute these eigenvectors. And I'm going to use this to get an initial condition on a small periodic planar Lyapunov orbit. So the eigenvalue nu that we can get analytically, the period should be 2 pi divided by nu. I'm taking a displacement just to get, this is the initial condition for a periodic orbit. And then I guess I messed with it a little bit just to see what would happen. So I integrate this initial condition that's shown in red for what I think is one period, but you notice it doesn't close up at all. It does hit the x-axis again, and that's enough for my algorithm to work. So the algorithm that I'm going to use will find this time, and it calls this time of this x-axis crossing T1. So this is x naught g, means a guess. I'm using the same initial condition. And this function called Lia_diff_core implements the differential correction. And in this case, it only took 4 iterates, and it found the time of that crossing. So the time of that crossing, due to symmetry, is exactly half of the full period. So now if I say that is, so integrate for the full period, TPO is 2 times T1, and then integrate the equations of motion again, here's what I get. I get something that closes back on itself. So the differential correction works. And if we wanted to know what's the actual displacement, I think if I were to zoom in, I'd have to zoom in quite a bit to see any kind of problem with this. I don't know, because it's not perfect. I have to zoom in quite a bit to see anything. Okay, so when it came back, there's a little bit of a displacement in position, but if we calculate the full displacement vector in phase space, it's very small. So this is 10 to the negative 9 times something. So that magnitude is pretty small. I put in that it should be around 10 to the negative 10, and it pretty much is. So now I use this code that this thing called PhiGet computes capital Phi. So phi at time t, this is the monodromy matrix. And you can see what it is. It's 10 to the third times a bunch of things. We can get the eigenvectors. And I guess I knew ahead of time that the fourth one is the stable one. Let's see. If I write D and then rerun this, maybe it'll actually show us what those eigenvalues are. It's hard to even see. So let me do D1, 1, 1, D2, 2, D. It's got to be a simpler way to do this. D4, 4. And then plot that. Run that. Okay, so lambda, the large eigenvalue, is 2.67 times 10 to the third. So like I said, on the order of 1,000. And then there's 2 eigenvalues of that equal very close to 1. You notice this has got a little bit of an imaginary part. That's because this isn't exactly periodic. It's very close, but it isn't exact. It's close enough, and it does the job. And then this number down here is actually equal to, if I were to subtract 1 over D, well, let me just do 1 divided by D1, 1. You can see that they should be very close to the same. Yeah, it is. So these aren't all independent. They're related because of the structure of the ODEs is Hamiltonian, and this is just something you get. You get things in pairs that are reciprocal. So the fourth one is the stable direction. So I'm going to look at the fourth eigenvector. I'll normalize it just so that eigenvector equals 1. I'm going to take a displacement of 10 to the negative 5, and then set an initial condition that's that same initial condition, the corrected initial condition along the periodic orbit. And notice, right, it's got an x value and then only a velocity in y. This displacement is 10 to the negative 5. And then here's the stable eigenvector, normalized stable eigenvector. So if I'm going to start along the stable eigenvector, if I go forward in time, I'll go towards the periodic orbit. So first I'm going to go backward in time. That's why this t-span goes backward. And I go backward 2 periods. I'm going to integrate that, plot it. But then I'll also start with that same initial condition and follow it forward 1 period. And then plot the result. This is what I get. The L1 is over here. The periodic orbit that we found is this. You can't even see it on this scale very well. But there it is. If I were to zoom in, maybe you could see it. So that's our initial condition. And when we integrate backwards, and I'm plotting that in black, that's a stable manifold, or one trajectory along the stable manifold. So if I follow it forward, this takes me onto the periodic orbit. And then zooming out, you could see once you get away from L1, you can have very large motion. This is where the moon is. I'm not really showing the radius of the moon, but I don't think this actually hits the moon. And I integrated this backwards for 2 periods of the periodic orbit. Typically, these Lyapunov orbits are half, their period is roughly half the orbital period of the primaries. So half a month, 2 weeks. So this is as a period of 2 weeks, and then I followed this back for 4 weeks. And then I went forward, and going forward, just this thing is just winding onto the periodic orbit, so it doesn't do anything unexpected. You might wonder, why did it go in the direction of the moon and not in the direction of the Earth? Well, we could change this displacement. If we made this displacement negative, that means we'll be on the other branch. And I actually don't know what will happen if I do this, but I think it'll go now in the direction of the Earth. Okay, so around 0, 0 is where the Earth is. It's really hard to see. Got to zoom in to see what happened. But so now we're on the other direction, and you can see the stable manifold. As it comes in, it seems to slow down. It's like it slow down and then naturally just gets into this periodic orbit. So this, I think, is these are the fundamentals of how you can get the entire continuum that forms these tubes. Because if you could do this for one initial condition along the periodic orbit, if you were to go to some other point and then do a displacement, you'll get a different trajectory. There's other more sophisticated ways to do this, but this works. If you wanted to get a larger periodic orbit, right? Choose a periodic orbit that you want. Here, I just started with some initial condition and then differentially corrected it. Well, I could use this same initial condition, and what would I do? I would change the value of x a little bit. So maybe move this out a little bit and use differential correction. I'll get a slightly bigger periodic orbit. And then I can keep doing that till I have a whole family of periodic orbits and maybe pick the one I want. If you wanted a periodic orbit of a particular energy, you can do that as well. The nuts and bolts of everything is down here. It's just a bunch of functions that you could look at later. But this is how it works. Any questions or anything? The same thing will apply once we go to the 3 degree of freedom system and look at halo orbits. Halo orbits, you could, again, use differential correction, get the halo orbit, and there's a stable and unstable direction for the halo orbit, and you can compute all of this for halo orbits as well. That's all I had planned for today. I think the next thing would be the next parts of chapter 4, which would be looking at not just the periodic orbits, but looking at the inside of these tubes. So that's kind of more advanced. It's now doing this not just for one point, for a whole bunch of points, and then how do we take a Poincaré section and see what's going on the inside.
Dr. Ross, got a quick question. You said that time periods for these periodic orbits are typically on the order of 2 weeks for the Earth-Moon system, and then this large transit maneuver you said was like 4 weeks. Are those typical for that system? Is that a good rule of thumb?
Oh, I just chose the time of twice the periodic orbit just so we could visualize it. So if I write here T, PO, and then divide by 2 times pi. So remember, in these non-dimensional units, the period of the moon around the barycenter is 2 pi. So if I'll show this. Yeah, so this is actually smaller than 2 weeks. So 0.42 times the the period of the Earth-Moon system. And that's typical, that it's close to 0.5. I think the period will change as we go to larger orbits, and I don't know if it gets smaller or larger off the top of my head. But that's what we get for this.
Okay, thank you.
Yeah. So that was it for today. I'll share this in the Google Drive, and you could play with it and do what you want. Just a note of caution. I've edited some of this code. Like I said, it was written in 1997, and some of these things make it look like it'll work for the 3 degree of freedom system, but it won't. Yeah, there's some things like I don't have the right syntax for doing ODE 7/8 or doing any kind of integration when I've got a 6-dimensional phase space. So everything here, it's just been made to work for just the n equals 4. So this is the dimension of the phase space. But yeah, it's all here. And like I said, I'm not using global variables in the way that MATLAB probably wants me to. That's why I've got all these errors. And well, they're not errors, they're warnings. Like, watch out, you're going to have problems. Looks like I'm not even consistent about how I define U-bar. This isn't U-bar. This is using some other kind of older notation that I used 25 years ago called omega. But essentially, it's the same thing. Finding an axis crossing, x-axis crossing. I think there's better ways to do this, but I made my own function before there was, before MATLAB had something called events. I just set something that could find x-axis crossing. And then this thing called int integrates. Again, it only works for this case, not the 3D equations. And I don't even know what halo y does. Yeah, a lot of this stuff just, hey, it works, and that's enough. Maybe just for fun, I'm going to integrate this backwards 20 times and see what happens. It'll just start filling in the Earth region. And you typically get this 5-pointed star thing for very small Lyapunov orbits, because that corresponds to a certain resonance. I forget what it is, 5-2 resonance. Typically, the trajectories that are on the stable and unstable manifold are pretty close to some kind of resonance. Partially because no matter what your Keplerian orbit, it's going to be near some kind of resonance with the body. And resonances tend to form these closed, multi-pointed shapes in the rotating frame. If we were to look at this in the inertial frame, I'm not quite sure what we would get, and I don't have the code for that right here. But hopefully that helps you get started. So next time we'll talk about the rest of chapter 4. We've basically done sections 4.1 through 4.3. So next time we'll do 4.4, which is trajectories with prescribed itineraries. And then for the last meeting, we'll talk about the halo orbits in the 3D problem. So thanks. That's it. I will be signing off.
If you appreciated this video, please like and subscribe, or just wait and watch the next video in the series.